In the last video, we learned that the pressure at some depth in a fluid is equal to the density of the fluid times how deep we are in the fluid, or kind of how high is the column of fluid above us, times gravity. Now let's see if we can use that to solve a fairly typical problem you'll see in your physics class or even on an AP physics test. So let's say that I have a bowl. A bowl, let me draw the bowl. So this is my bowl. A bowl. And in that bowl, I have mercury. And then I also have this kind of inverted test tube that I stick in the middle of this is the side view of the bowl, and I'll draw everything shortly. Let's say my test tube looks something like this. So the test tube that I put in the bowl is something like this. And let's say I have no air in this test tube. There's a vacuum here, but the outside of the bowl, this whole area out here, this is exposed to the air, and now we are actually on Earth. We're actually in Paris, France, at sea level, because that's kind of what an atmosphere is defined as. So the atmospheric pressure. So essentially, the way you could think about it, the weight of all of the air above us is pushing down on the surface of this bowl at 1 atmosphere. An atmosphere is just the pressure of all of the air above you and at sea level in Paris, France. And in the bowl, I have mercury. And I don't know, mercury is like a silverish color. So I'll draw it as silver. So I have mercury. Mercury, it's flat. I know I'm not drawing it completely flat. Whoops. This is mercury. I want to do it so that I can actually use the fill tool maybe. I have to just make sure it has no holes in it. I think I had got rid of all the holes. Okay, let me see. Let me try to use my fill tool. There you go. And let's say that mercury, there's no air in here. It actually is going to go up this column a little bit, and we're going to do the math as far as, well, one, we'll see why it's going up, and then we'll do the math to figure out how high up does it go. So say the mercury goes up some distance. Right, this is all still mercury. This is all still mercury. And this is actually how a barometer works. This is something that measures pressure. So you can imagine, over here, at this part, above the mercury, but still within our little test tube, we have a vacuum. There is no air. Vacuum, one of my favorite words because it has 2 U's in a row. Anyway, what was I doing? Oh, okay, so we have this set up. So my question to you is, how high is this column of mercury going to go? How high is this column of mercury going to go? And first of all, let's just have the intuition as to why this thing is going up to begin with. So we have all this pressure from all of the air above us, and I know it's a little unintuitive for us because we're used to all of that pressure on our shoulders all of the time, so we don't really imagine it, but there is literally the weight of the atmosphere above us, and so that's going to be pushing down on the surface of the mercury on the outside of the test tube. And essentially, since there's no pressure here, the mercury is going to go upwards here. But now this state that I've drawn is a static state. We've assumed that all the motion has stopped, etc., etc., etc. So let's try to solve this problem. Oh, and a couple of things we have to know before we do this problem. It's mercury, and we know that the mercury, the specific gravity, and I'm using terminology because a lot of these problems, the hardest part is the terminology. The specific gravity of mercury is 13.6. That's often a daunting statement on a test when you know how to do all the math and all of a sudden you know what is specific gravity. All specific gravity is the ratio of how dense that object is, that substance, to water. So all that means is that mercury is 13.6 times as dense as water, right? And hopefully after the last video, because I told you to, you should have memorized the density of water is 1,000 kilograms per meters cubed. So the density of mercury, let's write that down, density, and that's the rho, or a little p, depending on how you want to view it, of mercury is going to be equal to 13.6 times the density of water. So times 1,000 kilograms per meter cubed. Okay, so let's go back to the problem. So what we want to know is how high this column of mercury is. So we know that the pressure, let's consider this point right here. Let's consider this point right here, which is essentially the base of this column of mercury. What we're saying is the pressure on the base of this column of mercury right here, the pressure at this point down, pressure down has to be the same thing as the pressure up, right? Because the mercury isn't moving, we're in a static state. And we learned several videos ago that the pressure in is equal to the pressure out on a liquid system. So essentially, I have 1 atmosphere pushing down here on the outside of the surface. I must have 1 atmosphere pushing up here. So the pressure pushing up at this point right here. We could imagine that we have that aluminum foil there again, just to imagine that, where the pressure is hitting. The pressure there is 1 atmosphere. So the pressure down right here must be 1 atmosphere. And what's creating the pressure down right there? Well, it's essentially this column of water, or it's this formula, which we learned in the last video. So what we now know is that the density of the mercury times the height of the column of water times the acceleration of gravity on Earth, which is where we are, has to equal 1 atmosphere, because it has to offset the atmosphere that's pushing on the outside and pushing up here. So let's see. The density of mercury is this, 13.6 thousand, so 13,600 kilogram meters per meter cubed. That's the density, times the height. We don't know what the height is. That's going to be in meters. Times the acceleration of gravity, 9.8 meters per second squared, is going to be equal to 1 atmosphere. And now you're saying, Sal, this is strange. I've never seen this atmosphere before. We've talked a lot about it. But how does an atmosphere relate to pascals or newtons and all of that stuff? So this is something else you should memorize. 1 atmosphere is equal to 103,000 pascals. And that also equals 103,000 newtons per meter squared, right? So 1 atmosphere is how much we're pushing down out here, so it's how much we're pushing up here, and that's going to be equal to the amount of pressure at this point from this column of mercury. And 1 atmosphere is exactly this much, equals 103,000 newtons per meters squared. So let's see. Let's if we divide both sides, well, we could just do all of the math. So if we divide both sides by 13,609.8, we get the height is equal to 103,000 newton per meter cubed over 13,600 kilograms per meter cubed times 9.8 meter per second squared. And what does that get us to? And notice, make sure you always have the units right. That's the hardest thing about these problems, just to know that an atmosphere is 103,000 pascals, which is also the same as newtons per meter squared. Now let's just do the math. So let me type this in. Well, I'll use the pointer. 103,000 divided by 13,600 divided by 9.8 equals 0.77. And we were dealing all with Newton. So height is equal to 0.77 meters. And you should see that the units actually work out, because we have a meters cubed in the denominator up here, we have a meters cubed in the denominator down here, and then we have kilogram meters per second squared here, and then we have newtons up here. But what's a newton? A newton is kilogram meter squared per second. So when you divide, you have kilogram meter squared per second squared. Here you have kilogram meter per second squared. When you do all the division of the units, all you're left with is meters. So we have 0.77 meters, or roughly 77 centimeters, is how high this column of mercury is. And you can make a barometer out of it. You can say, oh, well, let me make a little notch on this test tube, and that represents 1 atmosphere. and you can go around and figure out what the atmosphere, how many atmospheres different parts of the globe are. Anyway, I've run out of time. See you in the next video.